Good morning, friends. I welcome you to my lecture on electronic spectroscopy. In my earlier videos, I have discussed about microwave spectroscopy and Raman spectroscopy. So, with the background, today we shall move on to electronic spectroscopy, which is also called UV visible spectroscopy. It is called UV visible spectroscopy because we use ultraviolet and visible radiation, and it is also called electronic spectroscopy because upon irradiation of the sample with ultraviolet visible radiation, electronic transitions are induced. Hence, it's also called electronic spectroscopy. We learned in our earlier discussion that during microwave spectroscopy, the sample is irradiated with microwaves, and these microwaves induce transition of the molecules between rotational energy levels. And in IR spectroscopy, when the sample is irradiated or exposed to infrared radiation, the transition of the molecules between vibration energy levels are induced. Similarly, when the sample is exposed to ultraviolet and visible radiation, ultraviolet and visible radiations have higher energy than infrared radiation. Therefore, electronic transitions are induced, or the molecules are excited from one electronic state to the other electronic state. Hence, it is called electronic spectroscopy. Since electronic spectroscopy involves electronic transitions, let us try to know what type of electrons are involved in these transitions. So, in this video, we will be discussing about the types of electrons, types of electronic transitions, selection rules, and Franck Condon principle. So, let us discuss these topics one by one. So, first one is what are the different types of electrons involved in electronic transitions? When the sample is irradiated with ultraviolet and visible radiation. So, the electrons are sigma, pi, and n electrons. These are the various types of electrons that we come across in molecules. So, sigma electrons are found, are the electrons involved in sigma bond formation are called sigma electrons, and the electrons involved in pi bond formation are called pi electrons, and the non-bonding electrons are called as n electrons. So, these are the three types of electrons that we come across in molecules, and all these electrons are involved in electronic transitions. Okay, so when there sigma, pi, and n electrons, where do we find, or which type of molecules will have these electrons? So, if you consider alkanes, you consider any alkane where all carbon-carbon and carbon-hydrogen bonds are sigma bonds. So, alkanes will always have only sigma electrons, or in other words, saturated hydrocarbons will have sigma electrons. And when it comes to pi, if you consider alkenes which have a carbon-carbon double bond, or alkynes which have got carbon-carbon triple bond will have sigma and pi electrons. Or in other words, unsaturated hydrocarbons or aromatic compounds will have sigma as well as pi electrons. And n electrons which are called non-bonding electrons. Whenever in an organic molecule there are atoms like oxygen, sulfur, nitrogen or halogen, these atoms will have non-bonding electrons. So if you consider a carbonic compound, maybe ketones or aldehydes or esters or carboxylic acids, oxygen in carbonyl compound will have two lone pairs of electrons. Or if you consider amines, nitrogen in an amine will have a lone pair of electrons. And if you consider a halogen, there will be three lone pairs of electrons which do not take part in bonding. Such electrons are called non-bonding electrons. So, the three types of electrons that are found in different types of molecules are all involved in electronic transitions. Now, after knowing the types of electrons, now let us see what are the types of electronic transitions that take place during the exposure of the sample to ultraviolet and visible radiation. So the types of transitions are sigma to sigma star, pi to pi star, n to sigma star, and n to pi star. These are the four types of transitions that we observe in the UV visible spectrum of a compound. So what are these sigma star, pi star? We have learned in molecular orbital theory that atomic orbitals combine to give molecular orbitals. So when atomic orbitals combine to give molecular orbitals, depending upon the type of combination, molecular orbitals of different types, namely bonding molecular orbitals, anti-bonding molecular orbitals, and non-bonding molecular orbitals are formed. So sigma star indicates anti-bonding molecular orbital, and pi star also indicates anti-bonding pi molecular orbital. So sigma star and pi star are called sigma and pi anti-bonding molecular orbitals. So these anti-bonding molecular orbitals will always have more energy and higher energy than corresponding bonding molecular orbitals. So once we have an idea regarding the types of electrons and electronic transitions involved in electron transitions in UV visible spectroscopy. Let us see what would be the order of energy of these bonding and anti-bonding molecular orbitals. So this is sigma pi n pi star and sigma star. This is the order of energy of various bonding and anti-bonding molecular orbitals. So when you look at this energy level diagram, it's clear that the energy required for sigma to sigma transition is highest, followed by pi to pi star, then followed by n to pi star, and followed by n to sigma star. So these are the types of transitions that occur during electronic excitation. So looking at this diagram, it's clear that the order of energy for these transitions is sigma star to sigma star is greater than pi to pi star, which in turn is greater than n to pi star, which in turn is greater than n to sigma star. N to sigma star, then n to pi star. So these are the different types of electronic transitions possible when the matter is exposed to ultraviolet and UV, ultraviolet and visible radiation. And this electronic spectroscopy or UV visible spectroscopy is mainly used to study conjugation in molecules. As we learned in earlier sessions that no single spectroscopic technique tells us or gives us the entire information regarding the structure. Each spectroscopic technique uses certain information regarding the structure. So compiling the data obtained from various spectroscopic techniques, it is possible to arrive at the final structure of a molecule. So electron spectroscopy is mainly used to study the conjugation. So after knowing the types of electrons and the types of electron transitions, now let us see what are the selection rules. So we have earlier learned the selection rule in microwave spectroscopy, selection rule in vibration spectroscopy, selection rule in Raman spectroscopy, etc. So what are these selection rules? Selection rules help us in knowing the types of transitions that are taking place in a molecule whenever the molecules are subjected to a particular type of radiation. So in electronic spectroscopy, we do have certain selection rules. The first rule is a spin selection rule, given by delta S is equal to 0. That is, change in total spin quantum number is 0. So one of the rules or one of the selection rules is that during electronics transition there should be no change in the spin of the electron. So small s denotes spin quantum number, capital S denotes total spin quantum number. For example, if you have a pair of electrons like this, which is pair, or let us say it is in a singlet state. So this is ground state and this is excited state. So the first rule, selection rule, in UV visible spectroscopy states that there should be no change in the total spin quantum number. In the sense, whenever an electron is excited to a higher energy level, there should be no change in the spin of the electron. For example, so this electron with the clockwise spin is excited. So it is transferred to the higher energy level without change in its spin state. So this is the first rule. So the first rule says that there should be no change in spin of the electron during the electronic transition. So this is a singlet ground state, and this is a singlet excited state. For example, if the electron takes a transition with the inversion in spin, then the excited state becomes a particular state. This type of transition is not allowed. Okay, so this is one rule. Next rule is the Laporte rule. Laporte rule is usually applicable to metal complexes. So, what is Laporte rule? First, a sub-rule of this is delta L should be equal to plus or minus 1. It should be smaller than that. So, L represents azimuthal quantum number. So, the sub-rule under Laporte rule is that delta L should be equal to plus or minus 1. In the sense, the transition like S to S, P to P, D to D are forbidden because delta L becomes 0. So according to this rule, this type of transitions S to S, P to P or D to D are forbidden, whereas S to P or P to D transitions are allowed. So this is a sub-rule under Laporte. This delta should be equal to plus or minus 1. Second rule is that only such transitions are possible which are accompanied by change in parity. What is this parity? You will understand. So second rule is the change in parity. So this rule is applicable for molecules having center of symmetry. Now we call them as centrosymmetric molecules. So the molecules having center of symmetry are denoted by G, which stands for generate, and U stands for ungenerate. So the molecules having center of symmetry are called generate molecules, and which do not have center of symmetry are called ungenerate. And gerate is represented by small g, and ungerate is represented by small u. So rule says that only such electron transitions are possible which are accompanied by change in parity. In the sense, gerate to ungerate is possible. This is a allowed transition. Whereas G to the gerate to Z or ungerate to ungerate are forbidden. So these are the selection rules which govern electronic transitions in electronic spectroscopy. Now, so after knowing the electrons, different types of electrons and different types of electronic transitions, and the selection rules which govern these electron transitions. Now we shall move on to a very important topic, namely Franck Condon principle. So before going on to Franck Condon principle and its statement, let me try to explain what type of, how do these electrons take a transition. Because the molecules have translation motion, rotation motion, vibration motion and electronic motion. So during this electronic motion, there will be translation as well as rotation as well as vibrational motions also. And we have learned that the energy associated with translation motion is negligible compared to rotational and vibration energies and electronic energies. So total energy of the molecule according to Bohr-Oppenheimer approximation is equal to sum of rotational, vibration and electronic energies. And during rotational motion of the molecule, there is no change in bond length or internuclear distance. And during vibration, there is a change in bond length. So whenever the molecule, the atoms of the molecule are vibrating constantly, there is a change in bond length. Hence we call it as average bond length or average internuclear distance, because in a vibrating molecule, the bond length keeps changing. Therefore, during vibration, the atoms vibrate about a fixed position. So that fixed position is called average bond length or average internuclear distance, denoted by RD in some textbooks, or it is also denoted by RD or R0. That is equilibrium internuclear distance. So, what would happen to this bond length when the electron is taking a transition? Or in other words, when a molecule takes a transition from ground state to excited state, what happens to bond length of the molecule? So, before going to Franck Condon principle, let us see. When you consider potential energy curve, that is the Morse diagram. So you can draw the potential. This is the energy, and this is your internuclear distance or bond length. So in the ground state, let us say this is the potential energy curve, and this corresponds to equilibrium internuclear distance. In the sense, if I consider a molecule E, the distance between the centers of this molecule nuclei A and B is equilibrium internuclear distance, and we have vibration energy levels like this. This is the ground electronic state. Let us denote it by E naught. This is the ground state of electron. So the molecules, say that this is V is equal to 0, V is equal to 1, 2, V is equal to 2, V is equal to 3, V is equal to 4, V is equal to 5, so on and so forth, where V is vibrational quantum number. So when the molecules at room temperature are present in V is equal to 0 state. So V is equal to 0 state will be more densely populated at normal temperature. So, and this is the bond length. They are vibrating at normal temperature. And this will be the change in bond length. And when the energy is supplied, vibration energy increases, so the molecule vibrates with the higher frequency of vibration, and the bond length keeps changing. So as we move to higher energy, as the energy is gradually supplied to the molecule, vibration frequency increases and bond length also increases. So these vibration levels indicate the increase in vibrational frequency with the supply of energy to the molecule. So when such is the case, and the molecules are supplied with energy in the form of UV visible radiation, so the molecules take a transition, because UV visible radiations have got the energy sufficient to transfer or excite the molecule from one electronic energy level to the other. So when the sample is irradiated with UV visible radiation, Now the question arises. So to which vibrational state in the excited state does do the molecules take a transition? So with the increase in energy, the frequency of vibration increases. So bond length also goes on increasing during the vibration. So when the molecule is supplied with energy in the form of ultraviolet and visible radiation, the molecules take transition from a ground electronic state to higher electronic state. Now the question arises, to which vibration state in the excited state the molecule take transition into? So if I consider, so when we consider when the molecule is vibrating constantly, the probability of finding molecules can be shown like this. So this is the probability of finding the atoms during the vibration. Similarly, that type of probability is shown in the excited state. So this is the state of affairs in the ground state and excited state in E, not an even. These are again is equal to 0, is equal to 1, 2, 3, 4, 5, so on and so forth. So when the molecules are in the ground state here, when they are supplied with the energy, the molecule takes a transition. Look at here, this they take a transition vertically or perpendicularly such that it goes to the maximum state. It does not take a transition like this, where this type of transitions are forbidden. There will be always a perpendicular transition during the excitation of the molecule from ground state to excited state. So here in this diagram I have shown that the possible transition is from V is equal to 0 to V is equal to 4. This is the possible transition or having highest probability. So when we look into the electronic spectrum of this molecule under these circumstances, the spectral line due to the transition from V is equal to 0 to V is equal to 4 will have maximum intensity, whereas other transitions will have lower intensity. This is V is equal to 0 to V is equal to 4, or it will be V is equal to 0 to 3, or this will be V is equal to 0 to 2, this will be V is equal to 0 to 1. So the most probable transition here is from V is equal to 0 to V is equal to 4. This is V is equal to 0 to 4 transition. So this spectral line will be most intense. So in some other cases it could be V is equal to 0 to 3 transition, which would be most probable, and that would be an intense spectral line. In some other cases it could be from V is equal to 0 to 1 or V is equal to 0 to 0, which would be most probable transition, giving us the most intense line. So when there are so many probabilities of transitions having the highest intensity, the ambiguity arises. Here comes in handy the Franck Condon principle. So Franck Condon principle helps us in knowing the intensity of vibronic transitions. So with the help of Franck Condon principle, it is possible for us to expect which type of transition is most probable, which spectral line will be most intense. So coming back to Franck Condon principle, Franck Condon principle states that during the electronic excitation is so rapid that the change in bond length of the molecule is negligible. I repeat, Franck Condon principle states that the electronic transitions are so rapid that the internuclear distance of the molecule does not change during this transition. In the sense, when the electron is taking excitation, in the sense there is increase in energy of the electron or as well as a molecule. So when the energy of the molecule is increased by the absorption of UV or visible radiation, there should be increased frequency of vibration and there should be increase in bond length with increase in frequency of vibration. But Franck Condon principle says that the electronic excitation is so rapid, it takes only 10 to the power minus 15 seconds, that is 1 femtosecond. So electronic transition is so rapid, it occurs within 10 to the power minus 15 seconds and immediately comes back to the ground state. So the electronic transition is so fast that by the time electron goes to the excited state and comes back to the ground state, the molecule does not know whether that electron is transferred or not. So electron transition is so fast that the molecule is unable to identify the electron transition because the nuclei are so heavy that by the time the electron takes a transition and comes back to the ground state, the nuclei do not undergo any change in their bond length. So this is the statement of Franck Condon principle. So when the bond length does not change during the electron transition, potential energy diagram changes. Because electronic transition is so rapid that the bond length does not change or the molecule is unable to experience the electron transition. So the bond length does not change. Now the state of affairs of the most curve changes to this fashion. Because the internuclear distance or equivalent internuclear distance in the ground state and the excited state are the same according to Franck Condon principle. So when internuclear distance in the ground state and excited state are the same according to Franck Condon principle, so which transition is most probable in that V is equal to 0 to V is equal to 0 in the excited state is the given state. So according to Franck Condon principle, the most probable time transition and the most intense spectral line would be for V and V dash in order to differentiate this. So V is equal to 0 into V dash is equal to 0. This transition will be most probable time transition and the spectral line corresponding to this transition will be more intense followed by other transitions which are of weaker intensity. So Franck Condon principle helps us in predicting that V is equal to 0 to V dash is equal to 0 is the most probable transition and the intensity of the spectral line will be maximum. So this is a Franck Condon principle. Thank you.